welcome to our class. So, in the last class, if you remember, we have discussed the role of catalyst, that is the Metallocene based catalyst, that is the main catalyst, and also role as co-catalyst, that is the MAU or the boron based catalyst, which is also called as a Lewis acid based co-catalyst. So, we have discussed in depth what is the individual role of the catalyst and main catalyst and the co-catalyst, and we discussed the mechanism in detail. And we understood that how the Metallocene compounds act as a polymerization catalyst for olefin compounds, as example like ethylene, polyisobene and others. Similarly, we also discussed that what is the origin of the demand of the Metallocene based catalyst, what was the disadvantage of the very famous catalyst for Nobel Prize winning catalyst, that is the Ziegler-Natta catalyst. So, we discussed very detailed. Today, we will discuss one more very unique feature of the Metallocene based catalyst which make this category famous, and that is the stereoselectivity. As you remember, for the Ziegler-Natta catalyst, the stereoselectivity, the origin of the stereoselectivity was to understand the mechanism was really very difficult, and also to tune the stereoselectivity it's very difficult. As you saw that the titanium TiCl3, that is the active species of the polymerization catalyst, that is really very difficult to understand, because the stereoselectivity depends on the crystalline phases, and you see that beta TiCl3, that is the brown phase, that is the performance of that beta TiCl3 is poor than the alpha, gamma and delta. But the most advantageous and the unique properties of the Metallocene based catalyst that you can regulate the stereoselectivity by changing the structure and the symmetry, and how it is that we will discuss. So, today we will discuss about the symmetry of Metallocene and stereoregularity. So, you see these 2 points, okay, the 2 words, one is the symmetry and one is the stereoregularity. So, what is the correlation between this? Okay, how we can tune the stereoregularity by changing the catalyst symmetry and the catalyst design, that we will discuss in the following classes. So, the concept will cover the catalyst design, that is very important, because according to our need, we will design our catalyst choosing the right the ligands, the bridging units, and obviously the metal center, and the more specifically the changing the substituents on the CP or the fused CP ring, that we discussed. So, we will see that how the selectivity is can be correlated with the symmetry of the catalyst molecule, okay, and obviously we will try to understand that in which mechanism the polymerization propagates. If you remember that we discussed in the previous classes about the CSC, that is the catalyst site control, and CEC, that is the chain end control. So, how these 2 mechanism can be operated depending on the symmetry of the catalyst and the resultant polymers, which actually you are targeting for. Okay. So, now we are very clear, okay, that this kind of polymerization can be done by this catalytic system, that is the Metallocene, that is the most simple Metallocene based catalyst, and this is the co-catalyst, that is the Lewis acid, okay. And in the last classes we learned that this co-catalyst is very much important to activate the main catalyst. So, after activation, what you will get, you will, if metal is zirconium, then you will get this one. So, I am writing just as a CP, and here, so we learned in the last class that MAO has a dual role. First role is the activation, first role is the methylation, and the second role is the abstraction of the methyl to make the catalytic center is positive and as well as coordinatively unsaturated. So this is my back end side. So this is the active form of catalyst. Okay. Now how the polymerization happens? Okay, I just try to refresh your memory. Okay, so if you have now this the active catalyst. So as I told that this is actually the eta 5. Okay, and this is the positive charge, and you have a back end side here. So if I let's say do the polymerization of any prochiral molecule, as example like propylene, if R is equal to methyl, then what will happen? So it will undergo through a cyclic transition state like this one. So okay, and you have a CH2. Okay, so I am writing as this one. Okay, now this CH2, this is the alpha hydrogen. This alpha hydrogen can undergo a agostic interaction that is very unique with zirconium metallocene bent metallocene complex, that it can undergo the alpha hydrogen agostic interaction. We have seen that the beta H agostic interaction is very much common. Okay, then it actually undergoes through the reaction through a 4-member transition state, and this one, okay, like that, and then so this is the cyclic transition state. Okay, and then this will be as well the Cp. Okay, and now this one will be CHR and CH2, okay, and this will be the CHR, CH2, and this will be actually CH3, sorry, because that carbon is now, that hydrogen is now here, so this will be now CH3. Okay, okay. Now what you saw here, if you notice carefully, so what happened? So this alkene has been inserted here. So this is the alkene insertion. Okay, fine. Now, so this is the positive charge as usual, and then similarly what happened? So you have a CH2, now CH3, now you have the R here, and this hydrogen can again undergo the agostic interaction like here. Okay, and this is the way it will undergo the polymerization reaction. So it will be, so this is the basically the initiation step, and after this would be propagation step. Now remember here, so this will, if it is prochiral, so we discussed in depth in the last classes that it can undergo the reaction by attack, by rephase or psi phase. Okay, and if the catalyst is the chiral, then it will favor a specific attack either on re phase or psi phase, and that is the origin of the stereoregular polymerization following the catalyst site control. And if the catalyst, if it is n chain control, then the chiral environment after inserting to the last prochiral monomer will dictate the attack of the second monomer, and that is the chain end control that we have discussed in the last classes. Okay. Now, the most unique and beauty is that how we can make it the stereoregular polymers. Okay. What I have to do on the Metallocene, because you see that this Metallocene, the simple this Metallocene, this one, this is achiral. So there is no way that you can get the stereoregular polymer. This is obvious, very obvious reason. You have a plane of symmetry, okay, and here you have to have a knowledge about the axis of symmetry in the following classes. Plane of symmetry. And I am sure that you know, okay, that axis of symmetry we designate as Cn, and plane of symmetry we designate sigma. Sigma can be sigma h, sigma b, that is horizontal, vertical, all those things. Okay. Now, how we can make it the chiral catalyst or induce the chirality in the catalyst so that we can get the stereoregular polymerization. So there was a attempt to make the chiral polymer. So here the first one Kaminsky tried, that we discussed, that you put two different Cp molecules and two different the substituent of the zirconation, but very surprising that atactic polymer was formed. Not so in the molecule it looks like that there is no plane of symmetry, but what happens that due to the very rapid exchange and rotation of the these two Cp rings, it is that the exchange is so fast that it is faster than the alkyl insertion, okay, and that is the reason that there is no stereoregularity is observed in this kind of structure. Okay. So we have to do some strategy that how we can make this polymer as a how we can make this catalyst stereorigid catalyst, so that we can get a permanent chiral environment. How we can do it? Okay, very simple. We have to bind these two Cp rings. Okay, so just like a thread it two Cp rings, so that there is no rotation or exchange. Okay, so we are basically restricting its fast rotation and fast exchange. Okay, so you see that just simple we restricting by putting the bridging unit, just threading the two Cp rings, and then what will happen? You will make the stereo rigid molecule. Molecule means here it is the Metallocene molecules. Okay, so by bridging the two Cp rings, it's the easiest strategy. However, we can also make the non-bridged Cp Metallocene compounds with more strategistic design. So here you see that we can make the chiral catalyst. However, in the last classes also we told that to make the stereoregularity, the absolute chiral molecule is not necessary. It can also undergo the stereoregular polymerization by following the chain end control, that we will discuss later. Okay. So as you know, these are all falls in the category of ANSA Metallocene. That is means the two Cp rings are threaded by a bridging units. Okay. So to understand in more depth, let's take a case study, okay, where you see that these two CP rings are basically the indenyl CP rings, okay, and here you see that if you see very carefully that this one and this one is actually the chiral, because there is no plane of symmetry, because you see this CP and this one, okay, this benzene, this CP falls on the benzene ring, it does not fall on the CP ring. That means here in this plane, if you see, this is no plane of symmetry, no plane of symmetry. So it actually exists as RS form, and you can get a if you put a mirror, so these two are actually the enantiomers R and S, okay. So superimposable mirror image. Now if you see this one, so this is or like indenyl 2 ZrCl2, this is the composition of this catalyst, okay. Now if you see this structure, so this is actually, see these CP rings are, these CP rings has basically just fall on above each other. So that means there is a plane of symmetry, okay, exist. So this is, there is a plane of symmetry exist here, but here no plane of symmetry. So that means this is selective catalyst, okay, and with this one we will get the isotactic polymer. We will discuss later how we will get it. I am just now trying to give a flavor that same composition, same ligands, but how we can get a different conformer of the catalyst, okay, and what will be the difference in symmetry. So from, if you use this catalyst, you will get a isotactic polypropylene, no matter whether you use the pure R or pure S or racemic mixture, because in the racemic mixture both R and S will do the polymerization individually, okay. So you will get in both the cases like individual R or individual S or racemic mixture of RS catalyst, you will get the isotactic polymer. Why? What is the reason? Because in this case two active positions are identical, okay, and that's why what you will get, these are the homotopic. These two active positions means I am telling this one and this one, okay, these are the active positions, because your monomer actually in one side it coordinates and then it undergo the insertion to the other side, this side, let's say, okay. So that we discussed in the last classes. So you will get the isotactic polymers, okay. If you specially design, you can also get the you can make the two active position enantiotopic, and in that case you will get the syndiotactive polymers that you need to design or induce the special symmetry on the metallocene, that we will discuss in the next slide. Now you come to the third one, okay. So third one is obviously, you see that here there is a plane of symmetry. So this is basically the meso isomer of this indenyl zirconium Cl2 metallocene, and this one you will get the atactic polymer, because this is not a chiral catalyst, this is the achiral catalyst, okay. So in here you this polymerization will undergo through catalytic site control mechanism, and you will get the atactic polymer if your monomer is, let's say, propylene, prochiral monomer. So you will get the atactic PP. So with this example, you will see that if you design your catalyst, you can get a different type of the tacticity on the same polymers, okay. So this is a one example. We will discuss in a very strategic way how we can induce the chirality, and if I give one catalyst, okay, how you will know that what polymer I will get, or if you had target for a one particular tacticity, what catalyst you design or what catalyst you select for your polymerization. Okay, fine. So this one, as I here, okay, you saw here there are no plane of symmetry here. Okay, no plane of symmetry. There is the same molecule, actually I draw it here. Okay, and it has a C2 axis of symmetry that we will discuss in the following classes. So that you will get the isotactic polymers, because both binding sites have the same chirality and those are homotopic. Okay, now as I told that if you design in a very strategic judiciously, then you can also get the syntactic polymers. Okay, and what you have to do, let's see in this catalyst. Okay, so this catalyst you will see here, here the two CP rings, okay, are different but symmetric. Okay, the two ligands are different but symmetric individually. Okay, so you will have a, you don't have a plane of this plane of symmetry, you don't have this one, but you have this plane of symmetry. So this is actually achiral. Okay, because you have a plane of symmetry. Okay, in this case no plane of symmetry, so this is actually the chiral. This is the chiral molecule and this is the achiral molecule. Okay, now each binding site is locally chiral here. Okay, and two binding sites have opposite local chirality, and that's why this site and this site has a two opposite local chirality, and that's why you will get the syntactic polymers. Okay, you will not get atactic polymer, because here the two sides, because you don't have this plane of symmetry but you have this plane of symmetry, and the two binding sides, this one and this one, is actually have a local chirality and have the opposite local chirality, and that's why you will get the syntactic. That is, if one methyl is oriented as R and another methyl in the polypropylene, it will be, the neighboring methyl will be oriented as S. Okay, opposite direction. So RS like that. Okay, so if you design your catalyst, you can get the syntactic, you can get the atactic, and you can get the isotactic polymer. Okay, that is the most beauty in this Metallocene based kind of polymers. Okay, and you can use as a toolbox. Okay, that whatever you need, you select your catalyst and you do the polymerization, you will get your target polymers. Okay, now in many cases what happens, this tacticity also depends on the temperature, on also the solvent. Okay, and also sometimes depends due to various reasons, there you may observe some error. So we are like for isotactic polypropylene, all the methyl should be on the same orientation. That means we should get all like a R like that. Okay, according to the CIP priority rules. But many times what happens, there is a errorness. That errorness is due to the various reasons. Now this is also very important, because this is also helpful to understand that whether this polymer chain is undergoing through CSC mechanism or chain end control mechanism, whether catalyst site control or chain end control. So this error is also advantageous sometimes. Okay, let's try to understand what is this error and what is the relation between the type of mechanism, that is the CSC, okay, or CSC. Okay, so let's first consider the isotactic polypropylene. Okay, now if it is going through a chain end control, let's say, okay, so I am first targeting chain end control. Okay, so let's say for isotactic polypropylene, what is the ideal scenario, that all the methyl will be on the same direction. That means this CH2 will be M, okay, M, M, M. Now, suppose there is a error. Okay. So, this is my error. This is my error. So, error means you see that this one will now in a different orientation. Okay. So, if as it is a chain and control, that means the last inserted monomer will dictate the insertion of the next monomer. So, what will happen? This will, after this insertion, okay, this methyl will be on the same orientation as the methyl which was inserted as error. Okay. So, this error will be preserved. Okay. So, in this case you will see the error will be continued or persist. Okay. But in the side chain, that is the catalyst side chain control, what we will see that if you targeting for isotopic polymerization, now it is going on fine, no problem. Now, this is the error. Okay. Now, if you consider the catalyst side control, if you remember that the propagation for the stereoregular polymerization is induced by the chirality of the catalyst. So, it does not matter how the last monomer was inserted. So, this will actually now repair its error, but this one is error persists. Okay. So, you see that for catalyst side control, okay, if you are targeting for isotactic polymerization, if there is a error, then that error will be repaired by the catalyst, repair of error by the catalyst through CSC. Is interesting, no? Yes, very interesting. Now, shown here in a very simplified way, that is the called line drawing. Okay, we have learned in the last classes. So, this is the isoselective polymerization when both CSC and CSC, that is the side chain and end control, are operating. Okay, as I showed in the last slide, you see that this, if you consider this is the chain end control. So, here you will see this is my error. Okay. So, all will be first M, that is no problem, going fine. Now, this is my error, and then what happens as it is a catalyst side control. So, it is repaired again. So, it is now repaired, and this is the chain end control. So, it is not repaired, the error will continue. Error will continue. Now, this one, how you will identify? This can identify by proton and 13C spectra. Now, you will see here is a very simple calculation or observation. So, here you will see the error M, you see the so we learned in the last classes dyad, triad. Okay. And now, here you will see here the MMR. Okay. So, this is, I will change the ink, then it will be more easily understandable. So, here you will see triple M, this one, okay, MMRR, this one, okay. Now, MRRRM, okay. So, you see MRRM is 1 unit, this is 1 unit, okay. Now, triple MR, so this triple MR, this triple MR, so that means 2 unit, okay. And MMRR, if you go from this side 1, and if you go this side, then these also 2 unit, okay. So, by looking at very carefully the proton and C13 spectra, you will get to know that whether it is the polymerization undergoes through catalyst site control or chain end control. Okay. And in this case, if you see the what will be the error, you will see that MMR here triple MR and here MMR this one. So, this is basically same number. Okay. So, this one, so you will get this one 1 and this one you will 1. So, by looking at the intensity of the corresponding CH2 protons, okay, you will able to know that whether it is following the catalyst site control or chain end control. Okay. Similarly, for syndio-selective polymerization, if there is an error, okay, then for catalyst site control, you will see that for syndio-selective, so this is my R. So, in a alternate orientation of the methyl groups. So, R. Okay. Now, this is my error. Okay. See, this is my error. So, this one supposed to be here, but it is not there. Okay. So, as it is a catalyst site control, it will repair. Okay. So, here again you will see after this one, it is the repairing error. And opposite scenario happens for chain end control. Here there is no repairing, that will be continuing the error. Okay. And due to this one, what you will get? You will see that RRRM, that is this one, that is the MMRR, this one you will get the 2 units, this is also 2 units if you come from this side, and this one RMMR, that one you will get 1 unit. So, by looking at the intensity of the CH2 protons or that CH2 carbon, you will be able to know that whether it is undergoing through catalyst site control or not. And in this case, you will see the triple R M, this one, and RRMMR, that is the this one, the number of this kind of quadrats will be same. Okay. So, this is also 1, this is also 1. Okay. So, this is one of the way by proton and C13 spectra, although you need a high resolution spectra, at least 400 or 500 megahertz NMR spectroscopy, you will be able to know whether what mechanism it is undergoing. Okay. Okay, fine. So, some of the important points you have to consider for this kind of catalyst. One is that I will just very briefly I will mention that if we have titanium, zirconium or hafnium, okay, of the same group, and if you consider the same ligands, so always the zirconium actually shows the better activity and better stereoselectivity. Okay. Always titanium has less active and also less stereoselectivity. Okay. And hafnium also less active but increases isoselectivity. Okay. And another important point, that shorter bridge increases the activity but decreases selectivity. Why? Because if bridge is shorter, then your openingness, okay, on the active sites will be more. So, then there will be preferential attack of the whether the Re or psi phase, that will be the less selective, and due to that one your the bridging should be in a critical length. It should not be very short, and also it should not be really big long. So, you have to have proper design of the catalyst. Okay. So, these 2 points are also important for designing your effective catalyst, which will give the better activity and also the better selectivity. Okay. So, in today's class, what we have learned? We have learned how the symmetry dictates the stereoregularity. And is basically we learned the design of the catalyst by modifying the Cp and substituents. Okay. And we also discussed that the error in stereoregularity and its relation with chain N control and catalyst site control mechanism. So, in the next class we will continue the symmetry, the correlation between the Metallocene symmetry and the stereoregularity. We will discuss by case to case with a specific category of the Metallocene molecules, and then we will see what symmetry are there and what symmetries are responsible for getting the isotactic or syndiotactic or atactic polymers. Okay. So, see you in the next class, which will be very exciting, okay, and important. Thank you.